So in this session of signals and systems, we are going to study discrete time Fourier transform. Remember, in our previous sessions, we have studied discrete time Fourier series, which was applicable to periodic signals. But now we want to study the discrete time Fourier transform, which will be applicable to non-periodic signals. So let us start. Now, before we write the equation for the discrete time Fourier transform, let us revise our knowledge of continuous time Fourier transform. Remember, it was given by this equation: x omega is equal to minus infinity to plus infinity xt e raised to minus j omega t dt. And remember, we had studied that the frequency spectrum for a non-periodic signal is continuous. And I will just revise what we had explained at that time. We had shown this by first assuming a periodic signal, and let's say you have a periodic signal whose time period is 1 second. In that case, the fundamental frequency is 1 hertz, second harmonic is 2 hertz, third harmonic is 3 hertz. So the difference between the successive frequency components is 1 hertz. Now suppose you increase the time period to 10 seconds. Then this difference between successive frequency components reduces, it becomes 0.1 hertz. So as you go on increasing the time period, the difference between successive frequency components reduces, and as time period approaches infinity, the spectrum becomes continuous. So non-periodic signal you may consider as a periodic signal whose time period approaches infinity. So the frequency spectrum becomes continuous. Now this is the equation for the Fourier transform. Similarly, we had studied the equation for the inverse Fourier, and it is given like this. So what we are going to do, we have already developed these equations starting from the basics of the Fourier series. So for discrete time, we will simply write the equations using the analogy, because the basics we have already studied for continuous time. So for discrete time Fourier transform, the definition is like this: x e raised to j omega. So here inside the bracket, instead of writing omega or j omega, you write this. Basically, it is just a notational convenience, because after all, this discrete time Fourier transform will also be a complex function of frequency, just like continuous time Fourier transform. But it is written in this form for two reasons. One is you can immediately distinguish between discrete time and the continuous time Fourier transform. And second is that the relationship between the DTFT and a transform called as Z transform can be conveniently expressed for this reason. Anyway, so let's look at the analogy. This is from minus infinity to plus infinity, that is, time changes from minus infinity to plus infinity. And here discrete time is n, so n changes from minus infinity to plus infinity. And the analogous operation for the integral in continuous time is summation in the discrete time. So you got a sum here. Instead of xt, you have xn, and then e raised to minus j omega t. So instead of t, you have n, which is the discrete time index. Okay. So just as in this case, frequency spectrum is continuous, here also frequency spectrum is continuous, but not only it is continuous, it is also periodic. We will show that. But before that, note by analogy, you can also write the equation for the inverse Fourier transform in this particular form. Now, what we want to do is to show that frequency spectrum for the discrete time signal is periodic. This is something which is different than the frequency spectrum of the continuous time signal, which is not periodic. So this we are going to show by doing a little bit of mathematics. So this is the discrete time Fourier transform equation, which I have repeated for convenience. And now let us evaluate this by increasing omega by 2 pi. So both sides of the equation we add 2 pi to omega. So the right hand side, this summation remains as it is, n equal to minus infinity to plus infinity, xn remains as it is, e raised to minus j, and now you write omega plus 2 pi into n. And this can be expanded. So this can be expanded into these two terms, e raised to minus j omega n into e raised to minus j 2 pi n. Now note that n is an integer. So because of that, this essentially the phase angle is an integer multiple of 2 pi, which is essentially 0. So e raised to 0 is always 1. Therefore, the right hand side simply reduces to this part, which is same as the original equation for the discrete time Fourier transform. So therefore, the left hand side is equal to x of e raised to j omega, which means that the frequency spectrum is periodic with the period 2 pi. All right. So having studied this, let us now work out an example analytically to find the discrete time Fourier transform. So let us first assume that our n is minus 1, 0, 1. Only these three values, because our sample itself has three values. That is, the signal itself has three samples. So first sample, when n equal to minus 1, this is 1. When n equal to 0, this is 0. When n equal to 1, this is 1. Okay. So now let us substitute. So this is from minus infinity to plus infinity. But before n equal to minus 1, x is 0. And beyond n equal to plus 1, again x is 0. So n essentially changes from minus infinity to plus infinity. Instead of this, you need only n equal to minus 1 to plus 1. Then this xn e raised to minus j omega n. So let us now expand this summation and get the various terms. So when n equal to minus 1, x of minus 1 is 1. So this is 1. N is minus 1, so this will be e raised to plus j omega. So the first term becomes 1 into e raised to j omega. Second term is 0, because 0 multiplied by this is 0, so I have not written it here. Third term is when n is equal to 1, xn is again equal to 1, so 1 into e raised to minus j omega. So your discrete time Fourier transform is given by this equation, and since we know that e raised to j theta plus e raised to minus j theta divided by 2 is equal to cos of theta, we can write this equation in this form, more compact form, 2 cos of omega. In general, the Fourier transform will have a real part as well as imaginary part. In this particular case, you don't have any imaginary part as it happens, but in general you will have real and imaginary part. Okay, so since in general this is a complex quantity, the frequency spectrum has two plots. One is the magnitude as a function of frequency, and second is phase as a function of frequency. So let us write both these equations. This is our original equation. So mod of this will be 2 mod of cos omega. Note that cos omega itself will have positive values as well as negative values. But since we are plotting the amplitude only, this becomes mod of this. What about the phase? Now, although the imaginary part is 0, note that cos omega itself will be either positive or negative, which will mean that the phase will be either 0 or 180 degrees. So let us write the various equations for the phase angle. This will be equal to 0 when omega is between minus pi by 2 to plus pi by 2. Remember, in this range, your cosine function has a positive value, which means the phase is 0. But if you consider these two ranges, minus pi to minus pi by 2, this is negative. So the phase angle is 180 degrees or pi radians. Also, when omega is between pi by 2 to pi, again, this will be 180 degrees. So if we plot the amplitude spectrum and the phase spectrum both, note that this is plotted for one cycle of the spectrum, which ranges from minus pi to plus pi. Note this minus 3.14, this plus 3.14. So this minus pi to plus pi. This is minus pi by 2 to plus pi by 2. In this range, the phase is 0. And here, note that when you plot the amplitude spectrum in this range, of course, cos is positive. Now, beyond this, the original cosine function becomes negative. But since we are plotting only amplitudes, we multiply by minus 1 and write only positive, plot only the positive corresponding positive values. Okay. Now from minus pi by 2 to plus pi by 2, this is 0. Then from minus pi to minus pi by 2, this is 180 degrees, which in this case is minus pi, so that is minus 180 degrees. And from pi by 2 to plus pi, again it is 180 degrees, so it's plus pi. Now don't be confused by this. You cannot really distinguish between plus 180 degrees and minus 180 degrees. You cannot. So whether you write as minus pi or plus pi, the phase angle is essentially same. All right. So we have studied one example analytically and plotted the frequency spectrum, that is both amplitude spectrum as well as the phase spectrum. Let us now try to see how to write the program for plotting the frequency spectrum for a given discrete time signal. Now what we are going to do is to use FFT to calculate DTFT. Now you require some special procedure for doing this, because FFT is a function which is basically applicable to periodic signals, and DTFT is the Fourier transform from non-periodic signals. So therefore you have to do certain modifications before you can use FFT straight away. So let us study them. One is that you append large number of zeros to X. What is the reason for this? The non-periodic signal can be considered as a periodic signal with time period approaching infinity, that number of samples approaching infinity. Obviously, in practice you cannot append infinite number of zeros, but you append a large number of zeros. The larger the number of zeros you append, better will be the accuracy of the calculations that you do. To give you an example, suppose my original signal contains only 3 samples, 1, 0, 1. Then I add large number of zeros to this. How many? We'll see an example. Another important thing you should note is that FFT assumes that the time index starts with n equal to 0. But if n starts with a negative value, as in our previous example, our first value for n was minus 1. So you had minus 1, 0 and 1. But FFT assumes that it starts from n equal to 0. So therefore, what it essentially does, it shifts the signal to the right by appropriate number of samples, say p. So let me illustrate this. Suppose n equal to minus 1, 0 and 1. Then since you want the n to start with 0, this has to be shifted to the right by one sample. So this will become 0, 1, 2. That will be the various samples for n. And this means that your x is also shifted. So the values of x are shifted, in this case by one sample. Now delay in time domain, remember one of the properties of the Fourier transform is that delay in the time domain corresponds to phase shift in the frequency domain. And what is the value of the phase shift? Minus omega p. So you write in the terms of exponential, it's e raised to minus j omega into p, which in this case happens to be equal to 1, because all the values of x shift to the right by one sample. So the phase has to be corrected. So if xa is the phase angle that you calculated by using FFT, you will have to add omega p to this, because remember, when you are using FFT, you are actually calculating the transfer of the shifted function. So you are essentially adding minus omega p to the angle. So to correct that, you have to add plus omega p to the phase angle that has been already calculated. All right. So with this background, let us now look at the program. So this is our usual first line. Now I have chosen m equal to 1, 0, 2, 1. Why this number? I'll explain that shortly. Now xa is equal to zeros 1 to m. So many number of zeros I generate. I want to append them to x. So I generate my x. So my original signal is 1, 0, 1. And I append m number of zeros to this by concatenating xa here. All these zeros are. So these are 1, 0, 2, 1. And these are 3 samples. So the total number of samples in the modified x become 1024. 1024 is an integer power of 2, and FFT yields good results whenever the number of samples is an integer power of 2, and that is the reason I have chosen this, although this is not the only value that can be chosen. You can have other values as well. Then you calculate n equal to length of x, and therefore your frequency index is 0 to n minus 1. Then you calculate your FFT, xt equal to FFT x. Then since this only plots the positive side of the spectrum, we use FFT shift that we had studied in our last session. That is your FFT shift xd. And then you have to adjust your k. Again, we studied this in our last session. So this is adjusted to minus n by 2 to plus n by 2 minus 1. And corresponding frequency you can calculate by multiplying k by 2 pi divided by n. And once you have calculated w, then what you can do, xa is the angle of x. Remember, x is calculated from here, and its phase value is calculated by using the function angle, and this is the correction that you apply. Remember, you have to add omega into p angle, but p in this case is 1, and that is why you have omega into 1, that is omega itself. Finally, you calculate the magnitude by using the absolute function for x. Then it's a question of just plotting. So it's something we have already studied. So you plot to subplot 2 and 1, so w versus the amplitude, and then you plot w versus xa. So the rest of the lines you already know, they are basically for describing the graph. So let us now, when you run this program, this is the output you get, similar to the one that we have discussed before. This is our amplitude spectrum, and this is the phase spectrum. So in this session, we have defined what is discrete time Fourier transform. We have seen one example of analytic calculation, and we have also seen how to use the FFT in order to calculate DTFT through a program. So you have to do some modifications which we have studied, and that is all in this session.